Section 3.7, Implicit Differentiation. Functions can be defined explicitly, as in the function y equals x squared, where the function is always solved for y, or implicitly, as in the equation x squared plus y squared equals 16, where the functions are hidden inside of the equations. So in our x squared plus y squared equals 16 example, we have the two functions y equals positive square root of 16 minus x squared, and y equals negative square root of 16 minus x squared. So even though this whole equation is not a function, it is made up of two functions, and those two functions are just hidden inside of the equation somewhere. So we call that implicitly defined. In order to find the derivative of an implicit function, we can use implicit differentiation. Implicit differentiation is just the process of taking the derivative of both sides of an equation with respect to x, and then you're just going to solve for your dy dx term. So let's do some examples. First one, find dy dx if we have y squared plus 2y equals 2x plus 1. Let me grab my marker. Okay, so what we're going to do is just take the derivative of both sides, like I said before. So we're going to find dx of both of these sides. So the derivative of y squared, that would have to be the chain rule. That would have to be the derivative of u squared is 2 times u, as it is, to the 1 times the derivative of u. Well, derivative of y is dy dx. dx plus 2y. So a constant times a function. Well, derivative of a constant times a function is just that constant times derivative of that function. Well, derivative of y, again, is just dy dx. Equals derivative of 2x is 2, and derivative of 1 is 0. So it just equals 2. Right, so if I have x, and I take the derivative of it with respect to x, right, well then this is dx over dx, right? Multiplying, right, we're taking d dx of x, so that's the same thing as dx dx, well, that is just 1, right? If I start with y, and I take the derivative of it, well then that is dy dx. It's the derivative of y with respect to x. Okay, so that's what I'm doing here. So that's why if I have x, it's just 1, and if I have y, well, it's dy dx, because here I have dx over dx, which is 1, or in other words, the slope of y equals x is always 1, and the slope of y, well, I don't know, it's just the slope of y, because I don't know what that function is. Okay, so now all I need to do is solve for dy dx, and as you can see here, I have two of them. So therefore I want to factor out the dy dx. So you get dy dx times 2y plus 2. Of course I could have divided everything by 2 first, but we'll do this first. Equals 2. And then I divide everything by 2y plus 2. And I just get dy dx equals 2 divided by 2x plus 2. Oh, 2y plus 2, sorry. And that's the same thing as 1 over y plus 1. Good. And as you notice, right, your derivative is in terms of y. Okay. Some of them will be in terms of x and y, some will be in terms of just x, some will be in terms of just y. Okay, next example. X times sine of 2y equals y times cosine of 2x. So I have the product rule on both sides of my equation. So the derivative of x first is 1, I'll write out every step, times, keep the second as it is, so sine of 2y, plus x as it is, times the derivative of sine of 2y. Well, derivative of sine of u is derivative of sine, which is cosine of, keep the inside the same, we're doing the chain rule, times the derivative of the inside. Derivative of 2y is 2 times dy dx. Okay, so don't forget all your rules from before. Equals, product rule again. So derivative of the first, so derivative of y, whoa, which is dy dx, times the second one as it is, cosine of 2x, plus the first one as it is, y, times cosine of 2x. Well, I have to do the chain rule. Derivative of cosine is negative sine, do parentheses then, so negative sine of, keep the inside the same, times derivative of the inside, well, derivative of 2x is 2. Okay, so now I just need to simplify this, and then I will solve for my dy dx, even though I have one on either side. So I have, let's see, I have a lot going on. Okay, so this is sine of 2y plus 2x, and then the dy dx and cosine of 2x, so 2x dy dx times cosine of 2y. Equals 2y dx times cosine of 2x minus 2y sine of 2x. Okay, so now what I'm going to do is put everything that has dy dx on one side and everything else on the other side. So I have, and then I'm going to factor out the dy dx. And since it's hard for me to write, I'm going to do that in one step. Also because there's a weird man in my house. So dy dx times 2x cosine of 2y minus cosine of 2x equals this one, which is negative 2y sine of 2x minus sine of 2y. Let's see, hopefully I did that correctly. Looks right to me. Okay, so now all I need to do is divide by this whole term here. Hopefully you can't hear anyone in the background. Dy dx equals, some things are multiples of 2, but not everything, right? This is not a multiple of 2, this is not a multiple of 2, so I can't factor the 2 out. So all I can do is leave it like this, which is not very pretty, but at least it's right. So negative 2y sine of 2x minus sine of 2y, all divided by 2x cosine of 2y minus cosine of 2x. And that is our answer. And so this is an example of one that is in terms of both x and y. Whew. Okay. One more example. Now we want to do the exact same thing, only I want to go one step further and actually find the equation of the tangent and the normal curves to the tangent and normal lines to this curve at the point 2, 3. So derivative of the first, so derivative of x squared is 2x plus, this is the product rule, derivative of the first is 1 times, leave the second as it is, plus the first as it is, times derivative of the second, which is dy dx, derivative of y, minus Chain rule, 2y to the 1 times dy dx, right? Derivative of the inside. Right? We're saying derivative of u squared is 2u to the 1 times derivative of u. Well, I have 2y times derivative of y equals, and then derivative of 1 is 0. Okay. Now, okay, so I need to put these two on one side and then the other two on the other side. And I'm going to, again, factor out the dy dx. So dy dx times x minus 2y equals negative 2x minus y. And let me just check this since I don't have anyone to check me. Then I have dy dx equals negative 2x minus y all over x minus 2y. Okay, so there is my derivative, which looks kind of crazy, but hey, it is totally cool. Let's switch to a different color. Let's go green. So now what I want to do is find the slope of the tangent line at 2, 3. So I need to plug 2, 3 into this function. So therefore I'm going to evaluate the derivative at 2, 3. So the notation for that is dy dx, vertical line, subscript, oops. If I just wanted to plug in x equals something, I would write x equals 2 here. But I can't do that because I have both x and y here. So let me change this. Oh, come on. Let me change this to the actual point. So this is at 2, 3. So dy dx evaluated at 2, 3 is plug in 2 everywhere you see x, and then plug in 3 everywhere you see y. So negative 2 times 2 minus 3 divided by 2 minus 2 times 3 equals negative 4 minus 3 is a negative 7. Negative 2 minus 6 is negative 4 equals positive 7/4. So the slope of the tangent line at 2, 3 is 7/4. Okay, so I'm going to use this to find the equation of the tangent line and the equation of the line that is normal to the curve. So this part should be easy because my tangent line is just going to go through the point 2, 3 and have the slope of 7/4. Let me check this. I feel like I may have made a mistake. It looks good. It looks good. Let me know if there's a mistake anywhere. So I have y minus 3 equals 7/4 times x minus 2. And that is my tangent line. Tangent. And for the normal one, all I need to do is take the opposite reciprocal of the slope. And it goes to the same point on the function. So I go y minus 3 equals negative 4/7 times x minus 2. And that is the line normal to the function, or perpendicular. But to sound fancy, we call it normal. Normal. There we go. So there are my two lines. Okay. And that is it. Here is your homework, these 3 questions. They should be very, very similar to what I just did. These two are just finding the derivatives using implicit differentiation, and this one is doing exactly the same thing that I did in this last example, which is finding the equation of the line's tangent and normal to the curve. So I hope this makes sense. I will see you tomorrow.